What's up, giggity gamers? Today we're sliding into the DMs of the most fundamental part of our universe, quantum physics.
Oh my god, it's Albert Einstein! It's Albert Einstein!
I ain't playing. If the only thing you know is Phantom Tax Cup, we good. So grab a bag of tacos, sit back, hit this clip. This is Quantum Physics Explained for Gen Z. Picture this, when you're vibing with bro on Snap, those notification dings are transmitted from your phone to your ear by vibration. Wait, hang on, pause. We gotta, gosh darn it, we gotta add subway service. The air moves back and forth, and when stuff moves back and forth like this, they're called waves. Now, think about photons, the smallest units of light. Moving in waves, or are they, plot twist, are actually both waves and particles, and neither at the same time. What the frick, dude? Okay, pal, but what are they made out of? They're like tiny energy-packed crocs, but without the gibbets. Gibbets? I don't know how to say. For real, that's a pretty hot take, but to demonstrate these really goofy shenanigans, we can set up a plate with 2 slits cut out of it. Then we chuck a detector screen right there, and our good old flashlight, except it has res to the power of -10, so it's like really small. This is called the double slit experiment. When the photons are fired through at random in the form of a beam, what do you think would happen? This? Wow. On the other side of this plate, the photons behave like waves, and the peaks in the waves that cross over the peaks in the other photons form bold lines on the detector screen, and the dips that cross with the peaks, they cancel them out. But that's trivial. So the end result is quite different from this. But okay, so they act like waves when you beam them? You're not that guy, pal. Even when sent individually, and one at a time. After a quick Insta-reel scrolling session, bro, look at this. It's the same. That's wild. That is just wild. Why is it wild? Because it implies that the effects you observe on photons interfering happens when there's just one particle. It self-interferes as if it went through both slits. Okay, so you set up separate sensors at each slit, and you fire a single photon through. What is this voice crack? And you fire a single photon through. True lack of any cap, it just went through wrong. So what has happened so far? When we don't observe the photons, they do a little bit of trolling and form what is known as an interference pattern. But when you send them one at a time and don't observe them, they do the same thing, which makes you think that they went through both slits at the same time. But when we detect them going through the slits, these guys are wacky, bro.
The animatronic characters here do get a bit quirky at night.
And it's not just photons that have wave-particle duality. Pretty much all of the fundamental particles. And something called a buckyball. A buckyball. What is that name, bro? Grab your cat now, we're putting it in this box. Why? Because some dude called Schrödinger wanted to prove how ridiculous superposition is. What are the concepts? This ocelot is chilling until it's dead. But you don't know when it's gonna happen because a decaying particle is about to release some energy at any given time, and that'll trigger as a poison thing. The idea is that the cat is both alive and dead at the same time. And it isn't neither. Until we open the box, that is. Once this happens, we have observed the system. Now, if you remember about 40 seconds ago, this is exactly the same as observing the photons. Right, that makes sense. No, it doesn't. Not really, no. But there is maths behind this, and we love maths, so here it is! Heisenberg's uncertainty. Nah, just tripping. Okay, so this on the left here means the spread of possible positions of a photon. Then that is multiplied by the spread of possible amounts of momentum, and all that is greater or equal to the Planck constant. So, said resolution depicts how the more we know about where a particle probably is, the less we know about how it's moving. So that's bad. We pretty much got ooga booga brains, because we actually don't know what is happening with these small particles. Now, the mathy boys weren't very happy with this, particularly Schrödinger, so we came up with this. The quantum wave function. Not only are the particles like waves, when their properties are mapped onto a graph, they form a wave as well. The driving factor behind all of this is the fact that quantum entities are inherently probabilistic. What am I cooking about? Don't worry, it is Slit. Because we don't know what these NPCs are up to, based off of measurements that we can do, we can plot a decently accurate chart to represent where these rows are at. But something real fancy schmancy happens when we overlap two-wave particle thingies, until something else comes along and causes decoherence. Coherence is when a quantum system is chill. You're chillaxing, you're fine, you're not being interfered with, and can complete their unique tasks. These tasks include entanglement, which is when two or more particles are in the same superposition. One particle's wave function has to be described with the others, so they are all sharing the same quantum state. This also means using the states of the particles, you can effectively instantaneously affect each particle, no matter the distance. But we can get to that in a future video. In conclusion, we've looked at wave-particle duality, the observer effect, which causes things to change between being a particle and a wave only when they're measured. Superposition, that states coherent particles are in all of their probable states all at once, and the fundamental concept, Schrödinger's cat, and Heisenberg's uncertainty principle. So, stay out of the TikTok doom scrolling, join the Discord server, and I'll catch you in the next one.